Welcome to the CMOS lecture series by KT Semicon. So in previous video we'll discuss the things completely related to CMOS, right? Why CMOS is that much popular in CMOS is where we are used CMOS, particularly in VLSI. All those things we'll discuss it, right? So in today's session we'll discuss the things related to semiconductors. Okay, some topics related to semiconductor physics, why silicon is widely used in VLSI, all those things. Okay, so let me share my screen. Yeah, I hope my screen is visible. So some fundamentals of semiconductor physics, like why only we are having so many metals or else in it, right? So why we are only choose silicon among all those things we'll discuss. Okay, so what are semiconductors? So we are using all in VLSA. We mostly use the semiconductors, right? So not only conductors, and insulators. Among them, we are using semiconductors. Why? So semiconductor is the material in between conductors and insulators, right? So if we are so here we are having three layers. Okay. So first one is conductors, semiconductors and insulators. So if we choose insulators means they cannot allow any kind of atoms in it. Even though when we are increasing the temperature also, it won't allow any kind of atoms in it. So in as compared to as coming to conductors will allow, even though it is in a very small temperature, very mini temperature also, it will directly allow atoms directly. We cannot stop the conductivity of electrons also. So that's why we need to minimize the both conductance and allowance of the atoms, which means in semiconductors we are having some limit. So if when we are applying the temperature, then only it will starts working. So whenever we are increasing the temperature, then only it will allow electrons in it, and then it will conduct. If you want to stop the conductivity also, we can do in semiconductors, but in conductors we cannot stop the conductivity. Okay, so that is the main drawback in conductors. And the coming to insulators, it won't allow any kind of electrons or else any atoms, even though when we are increasing the high temperature. So this is the drawback. That's why we are using semiconductors. Okay, so this is the main reason. Okay, so conductors means high conductivity. So high conductivity materials like metals like copper, silver or gold, it will easily conduct the current. Okay, so valence and conduction bands are overlaps. Why it will easily conduct the current means, so check it here. So these are the conductors. So it is having both valency band and conduction band. Okay, so there is no gap, there is no band gap in between conduction band and valency band. That's why even though we are at a 0 degrees temperature also, it will easily conduct the electrons. So from valency band to conduction band. Okay, so this is the main drawback in conductors. And as compared to insulator, very low conductivity. See here, so for insulators you are having more bandwidth. Even though when we are increasing the temperature in the valency band, these electrons are not moving from this valency band to conduction band. Why? Because there is more gap in between conduction band and valence band. Even though when we are increasing the temperature also, it cannot jump the electrons from valency band to conduction band. The main examples for the insulators are like rubber, glass. Okay, why? Because it is having more large band gap. Okay, so as coming to semiconductors, so semiconductors conductivity lies in between conductors and insulator, right? Not more band gap in insulators. Okay, so less space as compared to conductors. So the semiconductors are in between insulators and conductors. So conductivity can be controlled. See here, so we can control the conductivity. Whenever we want more conductivity, then we can increase the more doping, then automatically my concentration will increases, conductivity will increases. If you want to decrease the conductivity also, we can do. Okay, so that is the thing. And conductivity is sensitive to light and temperature, which means when we are increasing the temperature, then it will start conducting. That's why it is very sensitive to temperature. Okay, so this is the thing, semiconductors, which means, okay, and atomic structure and silicon. So why silicon is used means, so the silicon atom most common semiconductor material. Okay, second most abundant element in the earth crust. So that's why we are used. So in semiconductors also we are having so many metals, but why particularly silicon means, my silicon atomic number was 14. Okay, so if, whenever my silicon atomic number is 1, so we can check with electronic configuration. So here 1 is 2, 2 is 2, 2p6, 3 is 2, and in my outermost shell I'm having only 2 electrons. Okay, actually my outermost shell contains 3p6, but my atomic number was 14. That's why I'm having only 2 electrons in the outermost shell. Okay, so and the remaining 4 electrons is acts as the acceptors in the, I'll explain all these things. Okay, so here valence electron, 4 electrons in the outermost shell. So actually it is having 3p6 is the maximum value, but here we are having only 3p2. So if you want to add any electrons also we can add, because it is having 4 electrons in the outermost shell. Okay, sorry. Okay, from a stable covalent bond with 4 neighboring atoms to achieve. So if you want a stable covalent bond, then we need to add some more electrons in the outermost shell. Okay, so this is the thing. So here if you want to add electrons we can add. Okay, so there is a more, we can add 4 more electrons in this outermost shell. Okay, understand? So after that, energy band theory. Okay, we are having valency band, conduction band, and band gap. Sorry, guys. So these are the main things. Valency band means the range of energy levels occupied by the valency electron. So firstly, valency band is completely filled with electrons. Okay, so whenever we are increasing the temperature, then all these electrons in the valency band and try to jump from valency band to conduction band. Okay, so in conduction band, the energy levels where electrons are freely move and conduct current. So when my electrons are jumping from this valency band to this conduction band, okay, so now I'm having more space to move electrons from one side to another side. Okay, so whenever we are increasing the temperature, then my electrons are jumping from valency band to conduction band, and it will roaming into the conduction band, and whenever my electrons are moving means definitely it will conduct current. Okay, so this is the thing. And band gap, the forbidden energy gap between two bands, energy required to jump from valency band to conduction band. So what is mean by band gap? So the energy required to jump the electrons from valency band to this conduction band. So this is the gap, right? So here this is the gap. The gap in between covalent bond and valency band is known as band gap, right? So this is the thing. And so we are having silicon, germanium, and gallium arsenide. But why only silicon means? So if we select germanium, my energy gap will be less. See here, 0.67. If my energy gap is less, then what happened? It will start acting as a metal, right? So if my, for metals band gap is very less, right? So if my band gap is very less, then it can easily move the electrons from valency band to conduction band, and more conductivity happens, right? We cannot control that conductivity. Okay, so in gallium arsenide we are having more 1.43, which means it acting as the insulator. So even though when we are increasing the temperature also, electrons cannot jump from valence band to conduction band whenever we are selecting the gallium arsenide. So that's why we are selecting silicon. So for silicon we are having 1.12 electron volts band gap. Okay, so this band gap is enough. When we are increasing the temperature, then only it will start conducting. We can control the conduction also, right? So this is the thing. And intrinsic semiconductors, so we are having two different kinds of semiconductors: intrinsic semiconductors or extrinsic semiconductor. Intrinsic semiconductor means pure form of, see here, a pure semiconductor material with no significant impurities atoms. So here, so every atom is bounded with silicon atoms. Okay, right? So this is the pure crystal lattice. So this is known as crystal lattice. So in this crystal lattice, the crystal lattice is completely filled with silicon. So there is no impurities atoms in it. This is the complete silicon atoms. So at this time, number of free electrons is equal to number of holes, right? So whenever we are increasing the temperature, then one electron is trying to move from one place to another place, and again it will try to occupy this whole space. So and again this electron is move from here to here, and this will allow here. So like this happens. Okay, so whenever there is a hole, the electron is trying to occupy that space. So in this case, so when we are having pure silicon atoms completely filled in this crystal lattice, so this is known as crystal lattice, right? So that is completely filled with silicon atom, that is known as pure form of semiconductors, and number of electrons is equal to number of holes. And here my conductivity is low. Why? Because there is none. My electrons is equal to holes. Okay, if you want to conduct the current more, then we need to having more electrons, right? But here my number of holes is equal to number of electrons, so here my conductivity is very low. Understand? So at 0 degrees it is completely acts as the insulator, right? No electrons in the covalent bond, because so when we are having any free electrons means that completely that is filled with holes. So whenever we are increasing the temperature, then only it will throw one electron. Okay, before that my crystal lattice is completely packed, and there is no moving of electrons also at 0 degrees Kelvin. Okay, if we are having no moving of electrons means conductivity is also no conductivity, right? So thermal energy breaks covalent bond, generating electron hole pairs. So whenever at 0 degrees it acts as the insulator. So whenever we are increasing the temperature, then only it will start break the covalent bonds. So see here, it will break the covalent bond and it will try to occupy the another hole. Okay, so this is the intrinsic semiconductors, and after that extrinsic semiconductors. Okay, so extrinsic semiconductors means, so before that we are having pure silicon crystal, right? So whenever we are adding the doping with either p or pentavalent or trivalent atoms, so it will change it to n type semiconductors or else p type semiconductors. So when we are adding the trivalent impurities, okay, which means third group element. Okay, so whenever we are adding the third group elements, then it will act as the p type semiconductors. Okay, so whenever we are adding the pentavalent impurities, which means group 5 group 5 atoms like phosphorus or something, then it will act as the n type semiconductors. Why? Because so see, third group elements means, so up to now we are having in the outermost shell 3s2, right? If you want to fill that, we need to require 4 more electrons, right? So in third group element we are having only 3 electrons in the outermost shell, right? So even though when we are adding this third trivalent impurities, then one more. Okay, here 3, here 4, right? So then we are living with one hole in the outermost shell. So if you are having holes of creation means, then we can get the more holes in the silicon crystal, right? So when we are adding the trivalent, sorry, not this one, this one. Okay, so when we are adding the trivalent impurities in the pure silicon crystal, then we are having one extra hole in the outermost shell. Okay, so by combining all these holes, we can having majority of holes in the silicon crystal. Then what happened, it acts as the p type semiconductor. So when we are adding fifth group impurities, which means pentavalent impurities, so up to now we are having 4 electrons in the, we need to having only 4 electrons in the outermost shell. But when we are adding the fifth group elements, so we are having one more extra electron. That electron is ready to donate to the another one. Okay, so at this time we are having more number of electrons, right? So even though outermost cell is filled with this completely 4 electrons, After that also we are having extra electron. Okay, so by combining all the things we can having more majority of electrons, right? So in n type, in n type increases free electrons, and when we are adding trivalent to the p type, then it increases the holes. The process of intentionally adding impurity atoms to increase conductivity. Okay, so in intrinsic semiconductors we are having less conductivity. That's why we are doping. Okay, we are doping the impurities to increase the conductivity, right? So this is the thing. When we are adding the trivalent, then we can get the p-type semiconductors. When we are adding the pentavalent fifth group atom, then we can get the n-type semiconductors. Okay, so this is the thing, n-type semiconductors. So for n-type semiconductors we are adding pentavalent impurities. So here pentavalent impurities we are having extra one electron. That electron is acts as the donors. Okay, doping silicon 4 valency with phosphorus or arsenic. So 50 is the valency number, right? So that's why we are having one extra electron for donating. Okay, this acts as the donors, and here my majority carriers are electrons and minority carriers are holes, correct? So donor energy level is just below the conduction band. So at this time, electrons, this is my valency band, right? So this is the thing. So that's why my electrons is completely filled in valency band, right? That's why my energy level is near to this conduction band. Okay, why? Because my electrons are starts moving from valency band to conduction band, right? So see here, so here we are adding, okay, phosphorus, which means fifth group element. So after filling with all the bonds near to here, okay, okay, after completion of bond pairing, okay, it will having one extra electron here. See here, okay, here we are having one extra electron. This electron is acts as the donor. Okay, so this is the thing. That's why we are having majority of carriers or electrons in the n type semiconductors. Understand? So after that, p type semiconductors. Okay, for p type semiconductors we are adding trivalent impurities. So when we are adding trivalent impurities, then what happened? So when we are adding trivalent impurities in the outermost shell, up to now we are having 4 valency electrons. Sorry. Okay. So up to now we are having, okay, 4 valency electrons in the outermost shell. So when we are adding trivalent impurities like aluminum, boron, okay, okay, so then what happened? Even the outermost shell is having 4 valency electron, we are adding only 3 valency electron. Then what happened? We are having one more acceptor ion. Okay, one more. This acts as the hole means acceptor, empty space, it ready to accept the electron, right? So see here, see, we are adding aluminum here, then this bind is banding. Okay, here also group, but here we are having one more valency electron in the shell. So then what happened? This acts as the acceptor, which means hole. This is the hole, right? So this is the hole. Okay, it acts as the acceptor. Okay, that's why we are having majority carriers or holes and minority carriers or electrons in the p type semiconductors. Understand? So acceptor energy level is just below the valence band. So this is the thing here. And after that, p-n junction diode. So this is the p-n junction diode, right? This is the first experiment in every BTech student, right? In every electronics lab, p-n junction diode is the first thing, right? So how it will create? So up to now we understand how a p-type material is formed and n-type material is formed. So here we are combining both p-type and n-type, right? So here what happened? This is the p-n junction diode acts as the heart of electronics and formation. How it will how it will formed? So bringing the both p-type and n-type material together in a single crystal. So see here, so this is my single crystal. In this particular single crystal we are combining both p-type and n-type right? So in p type my majority carriers are holes, and here we are having more of free electrons, right? And diffusion of holes p2 and electrons or m2v. So here what happened, some recombination is happening here, right? So here recombination of electrons or holes are happening from when we are combining both this p type and n type, and these electrons are start moving into this p type. Okay, so here observe. So then there is a formation of depletion layer here, right? Okay, so here recombination is occurring at the junction, and formation of depletion region is happening. So when we are applying voltage at this p type or else n type, okay, so we are connecting here, right? Here these terminals we are connecting some voltage. Okay, so depending on this voltage it will starts working, right? So when we are applying the positive voltage to this terminal, then what happened? P type having holes. Holes means positive charge. So when we are applying the positive voltage, then it will start rippling, right? So even if you are applying some old positive voltage here, then what happened? So all these electrons are trying to move here. So depending on the applying voltage, then depletion layer width will increases or decreases, right? So in forward bias, what happened? My depletion layer is trying to minimize, which means depending on the voltage it will minimize the depletion layer. So when we are applying the reverse voltage, which means in the reverse biasing, then what happened, it will try to attract to the terminal voltage, and my depletion layer width will increases. So this is the thing happening here, and here we are having one built-in potential barrier also for this particular depletion layer. Okay, that is for silicon we are having 0.7 volts. So after increasing this 0.7 volt, then only it will allow into this depletion layer. Okay, so this is the thing. So here this is the forward bias. So for forward bias, p type is connected to positive side and n type is connected to negative side, right? So this is the thing, and it reduces the depletion width. Okay, so before that we are having some depletion region when we are combining both p type and n type. So when we are applying the positive voltage at p type and negative voltage to the n type, then what happened, my depletion width will decreases. Why? Because we are applying positive voltage at the p type, right? So and it lowers the potential barrier. Why? Because we are having only less width of this depletion layer. Okay, so at this time my current flow also easily happens because it lowers the potential barrier, right? So after that we are having reverse bias also. So for reverse bias we are connecting the negative voltage at this p type side and positive voltage to the cathode. So then what happened, there is a attraction of electrons and holes to the attraction of holes to this positive charge, and what happened, my depletion width will increases. Whenever my depletion width will increases, so we are having raise the potential barrier. So no significant current flow. Why? Because we are increasing the depletion layer. So this is the thing, and at this case we are having only less leakages. So this is the thing. So up to now, okay, so thank you.